Today my talk will be about hybrid model and model with continuous basis. We usually begin studying a model of algebra by consideration of linear composition of vectors, concept of linear independence, and basis. From the theory of representation of universal algebra, it follows that this consideration follows from wider concept of basis of representation. However, this concept does not work when we consider model or non-associative algebra. Solution of this problem follows from statement that model of algebra A is direct sum of copies of algebra A. This concept makes the connection between basis of model of algebra A and the basis of algebra A transparent. At the same time, direct sum imposes a constraint on the structure of model. The basis can be its most countable set. A set of non-zero coordinates of vectors is finite. If the algebra A is non-algebra, then we consider continuous homomorphism of model of algebra A. In such case, the requirement that the set of non-zero coordinates of vector is finite is incompatible with the definition of direct sum when basis is countable set. For instance, the limit of sequence of vectors 1.1 has infinitely many non-zero coordinates. Therefore, instead of requirement that finiteness of the set of non-zero coordinates of vector, we require that the expansion of vector will respect to the basis be convergent series. Today I invite you to an exciting cruise along different fields of mathematics. The final destination of our journey is the structure of model with basis, which is a set of power of continuum. Our first stop is model of algebra. Let V be a abelian group and D be commutative ring. The diagram of representation 116 is definition of model V over ring D. Representation G12 generates the model D, and representation G23 generates ring D. Similarly, diagram of representation 2.6 is definition of model V for the algebra A. And again, representation G12 generates the model A, and representation G23 generates the algebra A. We see the diagram 116 and 2.6 differ only in the type of universal algebra in the vertices of diagram. Vertex D of diagram of representation 2.6 is defined by diagram of representation 2.1. However, this statement is not significant when we study properties of a model V. In particular, ring D and the algebra A are examples of algebra. Therefore, we can consider more general definition of model and algebra. The following theorem and definitions are examples of recursive definition in linear algebra. We start from theorem to the 2. Ring of integers Z is Z model. First definition. Let Z be algebra. The model A is called algebra over algebra D or the algebra if we define product 2.2 where C is bilinear map 2.3. Next definition. Let algebra D be subalgebra of the center of algebra A. Effective left-side representation 2.4 of algebra A in the model V is called left model of algebra A. We will also say that the model V is left A model. The number is called vector. Bilinear map 2.5 defined by left-side representation 2.6 is called left-side product of vector over scalar. Similar way, we define right model of algebra A. Our next stop is topology of algebra. We assume that Z is non-algebra with discrete norm 3.1. Definition. Let A be a norm the algebra. Norm on left a model V is a map from model V into real numbers which satisfy the following axioms. Norm is non-negative. Norm of vector V equals 0 if and only if V equals 0. Norm of sum not greater than sum of norms, and norm of product vector over scalar equal product of norm of vector over norm of scalar. A model V endowed with the structure defined by given norm is called norm A model. Next definition. Let A be algebra over norm algebra Z. The norm on the model A such that norm of product not greater than product of norms is called norm on the algebra A. The algebra A endowed with the structure defined by a given norm on A is called norm the algebra. The set of considered definitions is example of recursive definition. Also, we introduce distance between A numbers by equality 3.3. According to the definition of norm algebra, the topology of the algebra A is the same as topology of the model A. This is why we consider topology of the model A, keeping in mind that corresponding definition and theorems are true for the algebra A. Definition. Let A be a norm the model. A number A is called limit of sequence AN if for any positive real epsilon there exists integer and zero depending on epsilon and such that distance between an and a less than epsilon for every n greater than zero. We also say that sequence an converges to A. Next definition. Let A be norm the model. The sequence an is called fundamental or Cauchy sequence if for every real positive epsilon there exists integer and zero depending on epsilon and such the distance between a p and a q less than epsilon for every p and q greater than zero. Norm the model A is called complete or Banach if any fundamental sequence of elements of the model A converges. Our next stop is definition of matrix over algebra. Let one be set of integers and let A be algebra. We usually represent the map for that 2 as finite table for that 3, which call matrix. Here I is index which numbers rows and J is index which numbers columns. We use Einstein summation convention in which a repeated index, one above and one below, implies summation with respect to repeated index. See quality 4.4. There exist problems where range of index may be countable or it can have the power of continuum. If a range of index is countable set, that we will assume the set of terms different from 0 is finite. If A is Banach algebra, then we will relax the requirement for the terms and we will require that the sum converges. If a range of index is continuous set, that we assume that there is measure on the range of index, and instead of sum, we write integral over range. we extend a Taylor summation convention, and we will mean integral of a repeated index, like equality 4.5. This convention will allow us to write expression which does not depend from a range of index. See, for instance, equality 4.4 and 4.5. We see that right side equalities is the same. If expression has indexes with different ranges, that expression may have form like inequality 4.6. Here we have sum over index I and integral over index j. We consider the operation of product of matrices. First definition. Let range of index of columns of matrix A be the same as range of index of rows of matrix B. Row column product or RC product of matrices A, B has form 4.7 and can be expressed as product of row of matrix A over columns of matrix B. If range of indices of matrices A, B are finite, we can write RC product as inequality 4.9. If range of index K has the power continuous, then equality 4.8 has the form 4.10. If algebra is commutative, the RC product corresponds standard product of matrices. Second definition. Let a range of index of rows of matrix A be the same as range of index of columns of matrix B. Column row product of matrices A and B has form 4.11 and can be expressed as product of columns of matrix A over row of matrix B. If ranges of indices of matrices A and B are finite, we can write CR product as inequality for 15. If range of index K has power continuum, then product of matrices has form for 14. Our next stop is definition of quasi-basis of algebra. Let D be algebra with the unit and A be the algebra. Then map 5.1 defined by equality 5.2 is the endomorphism of a abelian group A. The set A1 of maps A plus D is called unital extension of the algebra A. If algebra A is associative, then unital extension is also algebra. Definition. Let the algebra A be left a model of columns. If the set of A numbers 5.5 is the minimal set such that any A number has presentation 5.6, where Ci belongs to unital extension of algebra A, then the set A is called left quasi-basis of the algebra A. Let E be left quasi-basis of the algebra A, then the algebra A is direct sum of principal ideals 5.7. Similar definition we can leave for right algebra. Let the algebra A be right a model of columns. If the set of A numbers 511 is the minimal set that any A number has presentation 512, where Ci belongs to unital extension of algebra A, then the set A is called right quasi-basis of the algebra A. Let E be right quasi-basis of algebra A, then the algebra A is direct sum of principal ideals 515. If algebra A is commutative, we still tell about left and right quasi-basis of algebra A to make difference with basis of algebra A as model of algebra T. Before we consider quasi-basis of model, we consider theorem 6.1. Let A be the algebra, and let V1, V2 be a model of columns. Let EI be quasi-basis of a model VI. That set of vector 6.1 is quasi-basis of direct sum of a models V1 and V2. If quasi-basis EI are bases, then quasi-basis E is basis as well. Period. Let the algebra A of columns has left quasi-basis 6.9. Let left a model V be direct sum of copies of algebra A. Then left a model V has quasi-basis 611. This example of quasi-basis of model V, and you have matrix representation of quasi-basis. Next theorem. Let A be the algebra of columns. Let left quasi-basis in A of the algebra A be left basis. Then corresponding quasi-basis 611 of left A model V is basis as well. Our next step is differential geometry. Let B be Banach algebra and M be topological space. If there exists homeomorphism of topological space M into convex set N of the space B in power N, then homeomorphism F is called chart on the set M. If the map F is chart on the set M, then for any point M, there exists tuple M1, Mn of B numbers, which uniquely defines the point M. If there exist two chars F1 and F2, then the map F on commutative diagram 7.1 is homeomorphism. You can represent homeomorphism F of system of equality 7.2, where tuple x1, xn belongs to n1, and tuple 1, y1n belongs to n2. If map f1, fn has derivative of order k, then the map F is called diffeomorphism of class Ck. Definition. Let B be Banach algebra. The set M is called simple B-manifold of class Ck if for any two chars F1, F2, the map F on commutative diagram 7.1 is diffeomorphism of class Ck. Next definition. Topological space M is called differential B-manifold of class Ck if topological space M is a union of simple B-manifolds Mi and intersection of simple B-manifolds Mi, Mj is also simple B-manifold. Two-dimensional sphere is the simplest example of non-trivial differential manifold. There is no homeomorphism mapping sphere to the plane. However, we can consider sphere as a union of two hemispheres, for instance, union of northern hemisphere and southern. We assume that both hemispheres has common strip along the equator. Stereographic projection 7.3 is the ephemeromorphism of hemisphere to plane. Our next stop is definition of fibered model. Let A be Banach algebra, such there exists homomorphism of algebra B into algebra A. Let M be differential B-manifold of class C1. Then geometric object of Banach algebra A is geometric object of the differential B-manifold M. The measure mu is defined of the differential B-manifold M. Definition. Bundle A.1 is projection of topological space E onto differential B-manifold M. The differential B-manifold M is called base of bundle. The image of a point of the set M is called fiber. Different fibers are homeomorphic. We identify the smooth map field E and the bundle A.1. No example of bundles, for instance, set of planes orthogonal certain curve or tangent certain curve. Definition. Fibered A model is bundle P of V whose fiber is not a model V. An operation in model continuously depends on the fiber. Theorem. Fibered model is direct sum of fibers. Objects of fibered A model P are V-valued vector fields on manifold M. We meet vector fields when we study solution of differential equation. For instance, on the image A.2, we see fragment of phase space of specific differential equation. Let E of X be quasi-basis of a model V in fiber for point X. We assume that the map E is continuous almost everywhere. The map E is quasi-basis fibered A model P of V. V-valued vector fields on manifold M has expansion A.3 with respect to the basis E. We may consider two different types of homomorphism of fibered model. Fiber-wise homomorphism f of x. If there is basis E of fibered A model P of V, then matrix of homomorphism almost everywhere continuously depends on the fiber. At another type of homomorphism, a vector of a model V is geometrical object of algebra B. Therefore, differential transformation of coordinates of base of bundle generate fiber-wise homomorphism. Before we consider example of fibered model, I remind that Lie algebra S of Lie is the set of matrices of real numbers A.4, where product of set S of Lie is defined by quality A.5. Example, let segment minus 100, 100 be base of bundle. Let module of Lie algebra S of Lie be fiber of bundle. Let set of vectors A.6 be quasi-basis in fiber over point X. Quasi-basis of fibered module is defined almost everywhere except for point X equals 0 because this matrix turns to be 0 and X equals 3 because this matrix turns to be 0. Infinitesimal displacement generate passive transformation in fiber with matrix 9.1, where a set of maps gamma is called connection. Since passive transformation is infinitesimal, coordinate of vector change according to equality 9.2. Or we can write like equality 9.3. Equalities 9.2 and 9.3 are called parallel transfer. If fiber is right a module, then parallel transfer gets force of equalities 9.4 and 9.5. We also may consider Lie derivative of vector field in fibered module. Let field Vk manifold generate infinity-one transformation θ1, where epsilon is a real number. Let W be another vector field. Infinity-one transformation θ1 generate linear map θ2. From equality θ2, it follows that vector field W is transformed according to the equality θ3. Since vector W is differentiable, then equality θ4 follows from definition of derivative. According to definition of Lie derivative, we have equality θ5. And now we consider another example of model with continuous basis. Let V be left a model. Let the set 11, 1 be left with the basis of the algebra A. The map 11, 2 is called continuous Shauder quasi-basis of left a model V if the equality 11, 3 implies that A equals 0 almost everywhere. Similarly, we can define right quasi-basis of a model V. Remark, let I be finite set. I will remind that according to Einstein's summation convention, equality 11, 3 has form 11, 7. Here we see a significant difference from the finite-dimensional model. We require that coordinate of vector with respect to a basis of finite-dimensional model be uniquely determined. However, we cannot demand this for vector of model with continuous Shauder basis. We can represent a model V with continuous Shauder basis as direct sum 11, 8 of copies of algebra A. Theorem. Let V be left a model with continuous Shauder basis. Consider continuous map 11, 2 such that we have equality 11, 9. Then map E is quasi-basis of left a model V. Again, we have example of quasi-basis of left a model, and we have its matrix representation. If left quasi-basis of algebra A is basis, then the map E is continuous Shauder basis. To better understand the structure of model with continuous Shauder basis, consider a simple problem. Let the map F be a dimorphism of the model V. Let W belongs to V. To answer the question, where vector W belongs to an image of a dimorphism F, we have solved a linear equation 11, 11. However, when we write down the equation using coordinates, we get integral Fricke equation for the first type, 11, 12. Thank you.